Probability and Statistics, Chapter 8, Section 8.3, Estimating a Population Mean. If you remember, when you were estimating a population proportion, this is going to be very similar. So after this section, you should be able to state and check the random, 10%, and normal/large sample conditions for conducting this confidence interval. Two of them are the same, random and 10%. Normal large sample conditions a little bit different. Explain how the t-distributions are different from the standard normal distribution, why it's necessary to use a t-distribution. Determine the critical values for calculating a C% confidence interval for a population mean using a table and technology, your calculator. Construct and interpret a confidence interval for a population mean. And determine the sample size required to obtain a C% confidence interval for a population mean with a specified margin of error. So when sampling distributions close to normal, we can find probabilities involving X bar by standardizing. That's the z-score. Z equals X bar minus mu over sigma. But we have to divide by the square root of n, remember, because of the central limit theorem. So it's really divided by sigma over the square root of n. So we get the values of X bar on the left, and this is someplace besides at 0 on the right, the standard normal curve. So when we don't know sigma, we can estimate it, and we usually don't know sigma, using the sample standard deviation, S sub x. What happens when we standardize? Well, that means that we need to use the t-distribution. The t-distribution comes from a man who was developing this for a small set of data. He was working in a small brewery and called it student T distribution, because if he called it, if his company knew that he was using it, then he would have to give them credit for coming up with this, and I guess he wanted credit. It does have a different shape than a standard normal curve, but not much. It's symmetric. It has a single peak at 0. That's the same. It has much more area in the tails. And so this is what it looks like. The top one is the t-distribution. You'll notice it's X bar minus mu over S sub x divided by the square root of n. And the bottom one, X bar minus mu over sigma divided by the square root of n. So that difference, that change, the S sub x and the sigma, makes our curve a little wider at the bottom, the spread of the data. So t really tells us how far X bar is from the mean mu in standard deviation units, just like any other z-score, but it's now a t-score. And so we're going to have to use that idea and adjust things because of the width. This is a little bit different. There are degrees of freedom that we need to use. If you were picking sides for a basketball game, and first one side picks, and they've got a choice maybe of the 5 people standing around there, and then the other side picks, there is a point where you get down to where you got 2 guys left, and after that second to last person is picked, there is no degree of freedom. The last person goes with the other team. So our degrees of freedom will be n minus 1. I'm not sure that's the logic they used here, but that's what they found that they need to use. Whatever n is the size of your sample, if it's 10, you have to use 9. If it's 50, you have to use 49. So, also, the t-distribution with n minus 1 degrees will be t sub n minus 1. Conditions. So, simple random sample. Size n, large population, has a normal distribution with a mean mu standard deviation sigma. The statistic x, or t, uses x bar minus mu over s of x divided by the square root of n. That's the t-distribution stuff. With degrees of freedom n minus 1. When it isn't normal, this statistic will have approximately a t-distribution if the sample size is large enough. And we'll learn later 30 is the magic number. So when comparing density curves, standard normal distribution and t-distributions look pretty much the same, really. If you look at the picture on the left, the normal curve is that sort of dark purple one. The top one, if you look at the peak, it's the top one. The lighter sort of, I don't know, it's a blue, but not really blue aqua, whatever. It's the middle one. That is when you have 9 degrees of freedom. And the dashed one, the red dashed, is when you have 2 degrees of freedom. So the higher the degrees of freedom, the closer you'll get to the standard normal curve. And you'll notice how the dashed one down by the x-axis gets spread out a lot more. So there's more probability in the tails, and therefore the numbers are a little bigger than the z-scores, the z-stars that we've used. But as the degrees of freedom increase, it approaches that standard normal. So here's one way. What critical value t star from table B should be used in constructing a confidence interval for the population mean in each of the following settings? 95% confidence interval based on a simple random sample size n equals 12. Well, n minus 1 would mean use 11. And if you look at the table, you go to degrees of freedom in the left column, 11, and the the confidence level at the bottom, the upper tail probability we're going to use in the next chapter. The confidence level at the bottom, 95%. Where those two cross, the 2.201 is the t star. 2.201. Usually a 95% confidence interval. The z star is 1.96, if you'll remember. So 2.2 is a little bit bigger. That's because the base is spread out more. The x-axis is spread out more. What about a 90% confidence interval with 48 observations? Well, you use not 48, but 47. If you look at the table, it goes from 30 to 40 to 50. There is no 47. So what do? Notice the difference between 40 and 50. 1.684 for the 40, 1.676 smaller for the 50. So you want to make sure you include things. So you go for what they call the more conservative, wider interval, 1.684 for your t star. That way you make sure that you include this 90% stuff. It might be a little larger because it's not really 90%. But it doesn't make that much difference in the second, in the hundredths place. The difference between these two really is 0.008. So trying to be too accurate is not worth the worry, I guess. Corresponding critical value then 1.684, the more conservative. So these are the conditions. As with proportions, we have some conditions. Random. Usually it's stated in the problem. This comes from a simple random sample. 10%, same thing. Your sample size has to be less than 1/10 of the population, or 10 times the sample size. Your population must be at least that big. Normal and large sample, this is what changes. For a population to be normal, your sample size has got to be 30 or greater. Now, if the population starts out normal, you don't have to worry about it. It stays normal. But if you don't know, then make sure that n is greater than or equal to 30, or If you don't know and n is less than 30, then look at some things. The graphs of this stuff, the check for normality of the population. We had some procedures before. If there are any strong skewness or outliers, don't use the T procedures. So when conditions for inference are satisfied, the sampling distribution for X bar, roughly normal distribution. We don't know sigma. If we knew that, we'd probably be able to figure out what X or what mu is. We estimate it by using the sample standard deviation S sub X. So now we don't call it the standard deviation, we call it the standard error of the sample mean. S sub X over the square root of n. This is the same thing as we did before, really. To construct a confidence interval, same thing we did before. Replace the standard deviation of X bar by the standard error. Use S sub X instead of sigma. Divide by the square root of n for the central limit theorem. The T distribution, T stars, n minus 1 degrees of freedom in place of the Z critical values. So, statistic plus or minus critical value times the standard deviation of the statistic. The statistic is X bar plus or minus the critical value, use the T star, that's from table B, times the margin of error, the standard error, S sub X over the square root of n. So, one sample T interval for a population is similar in both reasoning and computation detail of one sample Z interval for a proportion. Same ideas, just different letters. X bar plus or minus T star, S sub X over the square root of n. And remember the distribution C percent, 95% to 90. The area is between negative T star and T star. So before we do this example, we'll need to go to the next recording. So I'm going to close this part out and we'll start another part.